Section 20.12, capacitors in series and in parallel. So we've seen resistors in series and parallel. Turns out capacitors are closely related, but just a little bit different. Let's take a look. So we'll start with them in parallel. If we have a battery and two capacitors, we know that each of these is going to have some amount of charge on it. Capacitors get charge Q on them. So instead of talking about the current, here we're going to focus on the amount of charge. So the total charge coming from the battery is going to be equal to the charge on 1 plus the charge on 2. We can relate that charge to the capacitance of each of these times their voltages, right? So Q is equal to CV. Each of them has their own capacitance, but each of them has the same voltage. They're both connected directly to the terminals of the battery to have the same V. So we can factor out the V, and this gives us a way to calculate the equivalent capacitance when they are wired in parallel. That's just adding the two capacitances together. So when you have parallel capacitors, you can get the equivalent capacitance by adding the capacitance, the individual capacitances. And that's what allows you to create this equivalent circuit that has a CP, a single capacitor that represents both of the individual capacitors. What about if they're wired in series? Well, if they're in series, what stays the same? With resistors, what stays the same is the amount of current that flows through the resistors. Similarly, with capacitors, what stays the same is the amount of charge on all the capacitors. So there's plus Q and minus Q on C1, plus Q, minus Q on C2. These all have the same charge. What's going to be different is they're each going to have their own voltage, V1 and V2. They'll take a separate, different amount of voltage from the battery. So we can take the overall voltage V, and that's equal to V1 plus V2 by Kirchhoff's loop rule, we now know. And we can rearrange Q equals CV to be V equals Q over C, right? This is just coming from our capacitance equation, Q equals CV. But now it's V equals Q divided by C. The Q is the same in both cases. The C is what's different. So if we factor out the Q, we get Q times the quantity, 1 over C1 plus 1 over C2. This is the inverse of our equivalent capacitance for series. So 1 over CS is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And that's how we can create an equivalent capacitor for all of the series capacitors. Notice this is the opposite rule as with resistors. When we have resistors in series, we're able to just add them directly. We don't need to do the whole inverse thing. And when we have resistors in parallel, we then have to add the inverse. So depending on if you have a capacitor or resistance, it's going to be a different rule. So I encourage you to make sure to write this out on your equation sheet. Series capacitor, parallel capacitor, series resistor, parallel resistor, because you do want to be able to keep this straight. So that's a brief introduction to capacitors in series and parallel.